All right, so let's continue our adventure in limits. Today we're going to look at continuity and how it relates to limits, and we're also going to do a thing called the Intermediate Value Theorem and how that connects to continuity. So let's jump in and get started. So what on earth is continuity anyway? So recall a couple of videos ago, we talked about one-sided limits, and I used this particular graph actually. So as x approaches 0 from the left, so that's over here. As we approach 0 from the left, what value are we approaching? Let me zoom in for you. It sure looks like we're approaching 1, the output of 1. So as x approaches 0 from the left, we're approaching 1. Now what about from the right? That's this one right here. What about from the right? Well, as we see, coming from the right, it's the same thing. It's 1. And what about the limit at 0? We said that that was 1. Even though the function doesn't exist there, the limit does. Even though the function doesn't exist there, the limit does. So I just kind of gave away the next answer. So what is f of 0? Since there's no closed circle, this does not exist. We've just determined that this graph is not continuous here, Now, what does continuous even mean? It means if you can draw the picture without ever lifting up your pen, then you've just discovered a region of the graph that is continuous. Now, see right here, so far it's continuous, but now I got to lift up and go around that, so that doesn't work. So we would say the graph is discontinuous at x equals 0. It's not continuous at x equals 0. This is called a hole in the graph, and it's a point of discontinuity, So lots of vocabulary there. So we say a function is continuous if, and only if, at x equals a, if and only if the limit coming from the left to the right are the same, and so therefore the limit at a is the same as where you thought you would be. Okay, so the function is where you thought it would be. Let me say that a little differently. The function is where you thought it would be. So I'm going to look at the same graph and ask you, is the function continuous at -3? Here's -3. So let me zoom in. Is the function continuous right here? Is the function continuous right here? So the limit there is what? So as we're approaching from the left and from the right, what is our limit? Our limit value is 4. And what is f of -3? It is also 4. So let's write that out. Yes, since the limit as x approaches -3 on f of x is 4, and that is also f of -3. So they all equal the same thing. So therefore, this graph is continuous at -3, x equals -3. So far we've been talking about continuity at a point, and we'll get to continuity on an interval here in a moment. So we can also turn it around, by the way. If I say that a function is continuous, if I just say, given continuous function f, then you know at a point, by the way, if it's continuous at a point, then you know this has to be true. So you can work it in converse as well. All right. So here's another graph that I used earlier in this series. So for what values of x is g of x not continuous? So the limit has to exist, and you have to be where you thought you'd be. So I would say it sure looks like we've got quite a few points of discontinuity. -2, x equals, let's write this down, x equals -2. Right here, do you see how the left and the right, they aren't equal? So therefore, that has to be discontinuous there. X equals 0. Anywhere else? I think we want to say x equals -5 even though that's an endpoint. I'm a little concerned because coming from the right, the limit there is 2, right? As we're approaching, we think we're gonna arrive at -2. But once we get there, there's an open circle. We never actually arrive. So I think we're going to call that a discontinuity as well. This side right here, this is over. Let me change colors so you can see it a little better. This region over here, that's all continuous all the time. All right, I was able to put my pencil down. I was able to draw the entire thing with never lifting up. So it's continuous on that interval. So let's write the intervals on which it is continuous. All right, so I already mentioned that right-hand region, but we want to start all the way on the left side. So from -5, I'm using a parenthesis because we're leaving that out, all the way up to -2, but I got to leave it out because, as I mentioned before, at -2 we have a discontinuity. So once we finally get there, it's actually discontinuous because it jumps down here. All right, we're going to union that with another region going from -2 all the way to 0, and then we have to skip that region again. And then we have a region from 0 all the way up to 5. And I think we can even put a bracket there and say let's consider it continuous at 5. Some could argue those endpoints might go a different direction, but let's go ahead and do that. So those are all the intervals where it is continuous. All right, so identifying the areas where it is, or the intervals where it is continuous, can help us understand this thing called the Intermediate Value Theorem. Students often ask me about this, so we're going to spend a little time on it now, and then I'm sure I'll make another video at some point on the Intermediate Value Theorem all by itself. So let's read this carefully. Suppose f of x is continuous on an interval. Okay, so you can imagine some sort of graph. So let's just go ahead and draw it. Let's call this A, and this will be B. Okay, so from here to here, the graph is continuous. All right, so I'm just imagining it as I go. Let M be any number between f of A and f of B. Now, what is f of A? Here is f of A. This number right here, this is your f of A right there. And then this number right here, if you go up and over, right, that's your f of B. Makes sense so far? Let's go back to that. What is that letter M? It says that letter M is going to be any number between here and here. Okay, so M is somewhere in between here. We haven't been given exact numbers, but we know that M is between. The Intermediate Value Theorem says, therefore, we know there must exist a C somewhere in between here and here, for which f of C is M. There must exist a spot, C, somewhere between A and B, such that f of C equals M. All right, it's a lot to digest, isn't it? It all hinges on the point that this is continuous. This doesn't work if the function's not continuous. If there were a break in the graph, we could not guarantee that everything gets hit. Now, I love to explain this with velocity. So imagine that you are at time, let me change colors here so it stands. I'm going to use the same graph here. So imagine that at time 1, you're walking, okay? You're walking 1 mile an hour. And then after 4 minutes later, so t equals 4, you are now basically running or jogging 4 miles an hour. So this is a velocity graph. It's a speed graph. Okay, so let's talk about this. So at the beginning of the experiment at t equals 1, you're going 1 mile an hour. And then what happens? You speed up, don't you? Like you start really moving quickly, and then you just kind of stay the same speed for a bit, and then you get going faster, stay the same speed, and then at the end of this experiment, they take a picture of you, and you are going 4 miles an hour. Now let me ask you this. Did you have to, or was there a moment in time when you were going 3 miles an hour? Was there a moment in time where just logic says you had to have been going 3 miles an hour? Yes, of course. Because between 1 and 4 seconds, you went from 1 to 4, and we're not doing any superhuman things here. We had to have gone through every single output number, every single y value at some point between 1 mile an hour and 4 miles an hour from second 1 or minute 1 to minute 4. Doesn't that make sense? You had to have been going 3 miles an hour at some point between A and B. It had to happen. That's the intermediate value theorem. And it only works if you're talking about a continuous function. And of course, your existence and your speed or your position or your acceleration, it's all continuous all the time. There are no radical jumps in it. And that's just how physics works. So let's look at an algebraic example here. It says, show that 5x squared minus 1 has a root on the interval 0 to 1. Now, we don't have to find the root, although I can show you how to do that real quickly also. So what does a root mean? You remember what roots are? Roots are x-intercepts. They are when y equals 0. So something comma 0. So you're trying to find an x value for when y is 0. That's what a root is. A root is also an x-intercepts. It's a solution to the equation 0 equals. So we're trying to show that this has a solution. We're just trying to show it with the intermediate value theorem. And we're also trying to show that one of them is between 0 and 1. One of the solutions is between 0 and 1. So here's what we're going to do. So at x equals 0, what do we have? We plug 0 into this. F of 0 is negative 1. So if you think about your t-chart, a lot of students like to visualize with t-charts. At 0, we are at negative 1. And here's that point right here. Boom. On my graph. Now we go to the other end point. The other end point is at x equals 1. So at x equals 1, f of 1 is what? Plug it in. You get 5 minus 1, which is 4. So 1 and 4. 1, 4. Now, is this a continuous graph? Yes, all polynomial graphs are continuous. You understand that this is a simple U-shaped parabola, right? We can put our pencil down and draw it anywhere in the graph. The entire graph is continuous all the time. So polynomial functions are continuous all the time. Not only in x squared, but in x to the third and x to the fourth. They're all continuous all the time. All right. So what are we looking for again? We're looking for a 0. We're looking for when y is 0. Do you see how 0 lies between 4 and negative 1? 0 lies right here. So there must exist some value a, or c, sorry, in between a and b, such that a 0 is output. So we would say, since f of b is greater than f of a, and, well, since it's continuous, and b is greater than a, and it's continuous, then there exists a c in between a and b such that some number between f of a and f of b is met. Now let me show you how you would actually solve for it. You would solve for the value c by doing this. You solve the equation like this. So often there's a part b that says, and find the value c that satisfies the intermediate value theorem. Find the value c that satisfies it. So you add 1, 1 equals 5c squared. C squared equals 1/5. You then hit it with the square root, and you see the answer is plus or minus the square root of 1/5. Now the positive end of that lies between 0 and 1. It's like right here, right? Lies right there. So the square root of 1/5 would lie between 0 and 1. But we knew it had to be. We knew it had to be because it's a continuous function. It was at -1, then it was at 4. Between 0 and 1, it has to hit every value in between. So there had to exist a value where y was 0. If you've worked with a TI calculator, you know this is true. You remember how you have it find a 0? You go a little to the left, a little to the right, and then it finds that 0 in the middle because it knows it has to exist if this is a continuous function. All right, so I think I have one more video lined up for you for this adventure on limits. So hopefully this has been helpful as you're trying to understand limits and get ready for that AP test or maybe that chapter test. Make sure you check out all the videos because I go through quite a bit about limits. I think it's going to be helpful for a lot of students, which was my goal. All right, until next time.